Okay, so at the previous lecture we proved the Nikolsky-Atkinson criterion for Fredholm operators. And today we discuss some corollaries and some applications of this result. So to begin with, let's recall the statement of this criterion, the Nikolsky-Atkinson criterion. Suppose that x and y are Banach spaces, and T is a bounded linear operator from x to y. Then the following conditions are equivalent. Condition 1, T is Fredholm. Condition 2, there exists a bounded operator, Fredholm operator. A Fredholm operator S from y to x such that TST equals T, and such that 1 minus ST and 1 minus TS are finite rank projections. That is very small operators. Condition 3, there exists a bounded operator S from y to x, which is essentially inverse to T, in the sense that ST is the identity operator modulo the compact operators, and TS is also the identity operator of y modulo the compact operators. In other words, the difference between ST and 1 is compact, and the difference between TS and 1 is also compact. And such an operator S is called an essential inverse of T. In general, the rule in operator theory is that when we use the word essential, we mean that something happens modulo the compact operators. So an operator is essentially invertible, even only if it is invertible modulo the compact operators, in this sense. So the equivalence between 1 and 3 is easy to remember. T is Fredholm, if and only if it is essentially invertible. Condition 4 looks weaker, but is equivalent to 3. There exist two operators, S1 and S2, from y to x, such that S1T is the identity operator modulo the compact operators, and TS2 is the identity operator modulo the compact operators. So roughly this means that T is essentially left invertible and is essentially right invertible. And this turns out to be equivalent to the essential invertibility. And moreover, so these four conditions are equivalent, and moreover, there is some additional information. Namely, if T is Fredholm and the index of T is 0, if the index of T is 0, then we can find a topological isomorphism S satisfying condition 2. There is a topological isomorphism S from y to x satisfying condition 2. This is precisely the part of this theorem which is due to Nikolsky. And in general case, the theorem is due to Atkinson. Also, if the operators S1 and S2 satisfy condition 4, satisfy condition 4, then they are essentially the same in the sense that their difference is a compact operator. Then S1 minus S2 is compact. Each of them is an essential inverse of T. S1 and S2 are essential inverses of T. So the left and the right turn out to be two-sided essential inverses. They are Fredholm. S1 and S2 are automatically Fredholm. And their indices are the same and are equal to minus the index of T. Okay, so this is the result which was proved at the previous lecture. And now let's look at some special cases and deduce some corollaries of this result. First of all, let's observe that the equivalence between 1 and 3 can be written in a more elegant form in the case where y equals x. So let's first of all recall that the set of compact operators on the Banach space is a closed two-sided ideal in the algebra of bounded operators on X. Is a closed two-sided ideal. So we can take the quotient of B of X modulo K of X. And this is a unital Banach algebra. Unital Banach algebra. So when we have a unital Banach algebra and quotient out closed two-sided ideal, then we get again a unital Banach algebra. And there is a special name for this algebra. This algebra is denoted by Q, script Q of X. And it is called the Kalkin algebra. Of the space X. So Kalkin was a mathematician who worked in operator theory and improved many interesting results about Fredholm operators and some related stuff. The Kalkin algebra plays an important role in, for example, in K-theory and in the extension theory of operator algebras. And we will use this algebra to introduce an interesting subset of the spectrum of a linear operator. So first of all, we have the following corollary. Corollary 1. If I have a bounded operator T on the Banach space X, then T is Fredholm. If and only if the respective element of the Kalkin algebra is invertible. Well, this is precisely the equivalence between 1 and 3 in the special case where y equals x. And now let's introduce an interesting subset of the spectrum. So we suppose that X is a Banach space over the complex numbers. Now, as usual, when this about spectrum, we work over the complex numbers. And we define the essential spectrum. The essential spectrum of T to be the set denoted in this way, sigma essential of T. This is a set of those complex numbers lambda such that the operator T minus lambda is not Fredholm. Is not Fredholm. Well, so it's clear from the definition that the essential spectrum is contained in the spectrum. If an operator is not Fredholm, then of course it is not invertible. Also, it's clear that if the space is finite dimensional, then the essential spectrum is empty, because all operators on a finite dimensional space are Fredholm. So what happens if X is infinite dimensional? Well, here's the answer, corollary 2. The essential spectrum of T is nothing but the spectrum of the respective element of the Kalkin algebra. Well, indeed, this is immediate from corollary 1. So as a corollary, we see that the essential spectrum, if X is infinite dimensional, so the Kalkin algebra is non-trivial, then the essential spectrum is compact and non-empty. Well, indeed, we know that the spectrum of any element of a unital Banach algebra, of a non-zero unital Banach algebra, is compact and non-empty. So the right-hand side here is compact and non-empty, and so the essential spectrum is compact and non-empty. By the way, there seems to be no simple way of proving this, there is no simple way of proving this which avoids using Banach algebras. Somehow, of course, it is possible, but the most obvious, the most simple proof is this. So we reduce everything to the Kalkin algebra, to the spectrum in the Kalkin algebra. Okay. Our next goal will be to show that the Fredholm property and the index are stable under small perturbations. So more exactly, well, first of all, let's introduce some useful notation. If X and Y are Banach spaces, then set of all Fredholm operators from X to Y will be denoted like this. This is the set of all bounded Fredholm operators. And if X equals Y, then we write just Fred of X. So now we have the following theorem. So let it be theorem 2. This is theorem 1, if you don't mind, and this is theorem 2. Theorem 2, the set of Fredholm operators is open in the space of all bounded operators. And the index is a function on the set of Fredholm operators to the integers, is locally constant. that is constant in the neighborhood of any point. Equivalently, we can say that this function is continuous, because z is discrete. So a function to a discrete space with values in a discrete space is locally constant if and only if it is continuous. Before we prove this theorem, let's recall one more simple fact from the theory of Banach algebras. So let's recall that if A is a unit of Banach algebra, if A is a unit of Banach algebra, then the set of all invertible elements will be denoted by A cross. The set of invertibles A is open in A. The set of invertibles is open. So now let's begin proving this theorem. We start with so the first step is the following lemma. So first of all, we will show that the set is open. The set of Fredholm operators is open. Well, of course, we can suppose from the very beginning that this set is non-empty. Otherwise, there is nothing to prove. We assume that this set is non-empty. Then I claim that the set of Fredholm operators from y to x is also non-empty. This follows, for example, from the Nikolsky-Atkinson criterion. So take any Fredholm operator here and take its essential inverse. So let's take any operator, any Fredholm operator from y to x. So we take any Fredholm operator from y to x and consider the following map. Consider the map F from the space of bounded operators from x to y to the Kalkin algebra Q of x. So F is given by the following formula. It takes T to St modulo the ideal of compact operators. So it's clear that F is a bounded linear operator. F is a bounded linear operator. So in particular, it is continuous. And let's now recall the following fact, which was proved some time ago. So we know that an operator T from x to y is Fredholm if and only if St is Fredholm. If S is Fredholm, we assume that S is Fredholm. So then T is Fredholm if and only if St is Fredholm. So this observation implies that the set of all Fredholm operators from X to Y is nothing but the preimage of the set of invertibles in the Kalkin algebra. T is Fredholm if and only if this operator is Fredholm, but this operator is Fredholm if and only if this element is invertible in the Kalkin algebra. So this completes the proof of lemma 1, because this set is open in the Kalkin algebra, and the preimage of an open set under a continuous map is open. Okay. Lemma 2. I claim that the set of all invertible operators from X to Y is also open. It's open in B of X, Y. The proof is very similar to the proof of lemma 1, so I'll leave it as an exercise for you. Basically, the only difference is that first of all, we choose an invertible operator from Y to X. If X and Y are not topologically isomorphic, then there is nothing to prove. Then we choose an invertible operator S from Y to X, and we consider a similar map F, which acts not to the Kalkin algebra, but just to B of X, and takes T to ST. And basically, we just replace the Kalkin algebra Q of X by B of X. And the proof is the same. Okay, so now we can prove that the index is locally constant. Proof of theorem 2. So we take a Fredholm operator, T, from X to Y. So we claim we want to find a neighborhood of T such that the index is constant on this neighborhood. Since T is Fredholm, we can always find the following direct sum decompositions. X is topological direct sum of x0 and x1. Y is a topological direct sum of y0 and y1, where x0 is the kernel and y1 is the image. This is always possible because we know that the kernel, we know that each finite dimensional subspace is complemented and each closed subspace of finite codimension is complemented. So these two subspaces are complemented, and so we can find such decompositions. Let's introduce two more operators. So let J denote the inclusion map from x1 to x. The inclusion map. And let P be the projection of y onto y1 along y0. Projection onto y1 along y0. So what can we say about these two operators? Clearly they are Fredholm. J and P are Fredholm. because x0 and y0 are finite dimensional. And P, Tj, this is a map from x1 to y1, is invertible. Well, this is clear because this operator is nothing but the restriction of T to x1. And clearly, it takes x1 bijectively onto y1, where 1 is the image of T. Okay, now we apply lemma 2. So we know that the set of invertibles is open. So lemma 2 implies that there is a neighborhood U of T in the set of Fredholm operators such that for each operator T, for each operator S in this neighborhood, the operator PSJ from x1 to y1 is also invertible. This follows from lemma 2 because when S is close to T, then of course PSJ is close to PTJ. So the difference between this and this is estimated as a constant multiplied by the difference between S and T. So if S is close to T, then this is close to PTJ. And so if the distance is small enough, then this operator is invertible. Well, it's invertible, so its index is 0. Its index is 0. PSJ, the index is 0. Well, we know that the index is the sum of the indices. P, S, and J are all Fredholm. So this is the index of P plus the index of S plus the index of J. And this holds for all operator S, for all operators S in this neighborhood. But of course, the first summoned and the third summoned, they don't depend on the choice of S. They are constant. And so this implies that this function, the index, is constant on U. And this completes the proof. So the index is locally constant. By the way, this property, theorem 2, is sometimes called the Homotopian variance of the index. This may seem a little bit strange because there are no homotopies in the statement. But the reason is that the main applications of this theorem are mostly related to the situation where we have two Fredholm operators which are connected by a continuous path in the set of Fredholm operators. And usually this path is given by is induced by some homotopy. And since the index is locally constant, this implies that the index will be constant along this path. We will meet, by the way, this situation fairly soon when we speak about Topless operators. Well, actually, there are at least two ways of giving a precise meaning to the notion of a small perturbation. So the first point of view is that the operator is small if its norm is small. And we just proved that the index is stable under small perturbations in exactly this sense. So if we add a small norm operator to our fixed operator T, then the index will be the same. And the second point of view is that the operator is small if it is compact. So let's now show that the Fredholm property and the index are stable under compact perturbations. this is theorem 3. Suppose that T is a Fredholm operator from X to Y, and K is a compact operator from X to Y. I claim that the operator T plus K is again Fredholm. And the index of T plus K equals the index of T. The proof is a simple application of the Nikolsky-Atkinson criterion. So let's take an essential inverse of T. We choose a bounded operator S from Y to X such that ST is the identity operator plus a compact operator, K1, and such that TS is the identity operator plus a compact operator, K2. I claim that the same operator S will be the essential inverse of T plus K. Well, indeed, if we multiply S by T plus K, then we get 1 plus K1 plus SK. And this operator is compact because K is compact and K1 is compact. And similarly, T plus K multiplied by S is TS, that is 1 plus K2 plus KS. And again, this operator is compact for the same reason. So we see that the same operator S is an essential inverse for T plus K. So the Nikolsky-Atkinson criterion, theorem 1, implies that T plus K is Fredholm. T plus K is Fredholm. And also we know that the index of this operator, T plus K, equals minus the index of its essential inverse. And the essential inverse is S. And for the same reason, the index of T is equal to minus the index of S. And so we conclude that the indices of these operators are the same. Let's now give a useful characterization of Fredholm operators of index 0. This will be theorem 4. This theorem is entirely due to Nikolsky. So again, X and Y are Banach spaces. And T is a bounded operator from X to Y. Then the following conditions are equivalent. Condition 1, T is Fredholm, and the index of T is 0. Condition 2, there exists a topological isomorphism R between X and Y and a finite rank operator, say K, a bounded finite rank operator from X to Y, such that T equals R plus K. In other words, a Fredholm operator of index 0 is a finite rank perturbation of a topological isomorphism. And condition 3 is similar to condition 2. There is a topological isomorphism R from X to Y, and a compact operator K from X to Y, such that T is R plus K. Okay, so let's show that 1 implies 2, first of all. To show that 1 implies 2, let's recall again the Nikolsky-Atkinson criterion. So T is a Fredholm operator, and the index of T is 0. We know that in this case we can find a topological isomorphism between Y and X by theorem 1. There is a topological isomorphism S from Y to X, which is essential inverse to T. Actually, we will use only the fact that it is left essential inverse, such that ST is the identity map plus not just a compact operator. We can choose S in such a way that 1 minus ST is a finite rank projection. So ST is 1 plus a finite rank operator, K1. K1 is a finite rank operator on X. At this point, it's not essential for us that K1 is a projection. It's essential only that it is a finite rank bounded operator. Let's not now just multiply this equality by S inverse on the left. So this implies that T equals S inverse plus S inverse K1. And that's it, because S inverse is a topological isomorphism between X and Y. And this is a finite rank operator from X to Y. Clearly, a composition of a finite rank operator and any operator is also a finite rank operator. Okay, so 1 implies 2. Clearly, 2 implies 3. This is obvious because the finite rank operator is compact. And the remaining application, 3 implies 1, follows from theorem 3. Well, indeed, we know that the index is stable under the Fredholm property, and the index are stable under compact perturbations. But of course, since R is a topological isomorphism, it is Fredholm, and the index of R is 0. So by theorem 3, the same is true of T. Okay, that's it. Well, so far, all the results, well, they are quite elegant, but at the same time, they are rather abstract. So our next goal will be to apply these results to a very concrete and useful class of operators, namely to Topless operators on the circle. So let's introduce some notation. First of all, we denote by bold T the unit circle on the complex plane, centered at 0. There is a canonical measure, the standard measure of the circle. Let's denote it by mu. And this is the normalized length measure. That is, this is the length measure divided by 2 pi. So that the measure of t is 1. This is quite convenient. So we will be interested in the space L2 of t, the big L2 space. So this is the usual space of square integrable functions on the circle with respect to this standard measure mu. This space has a classical orthonormal basis. Namely, let's denote by En the function on t given by the following simple formula. En of z is z to the power n. And the classical theorem, due to Weierstrass, implies that the linear span of these functions, where n runs over the integers, is dense in the space of continuous functions on the circle. This space, this linear span is the space of trigonometric polynomials. This is the same as the space of all Laurent polynomials on the circle. So it is dense in C of t by Weierstrass theorem. And since C of t, the space of continuous functions, is dense in L2 of t, this implies that this space is dense also in the space L2 of t. And moreover, it's well known and easy to calculate that this is an orthonormal family in L2 of t. So this implies that this space, the set En, is an orthonormal basis. An orthonormal basis of L2 of t. We now introduce the following important subspace of L2 of t, namely the Hardy space. The Hardy space of the circle is the space denoted by H2. And by definition, the space consists of those functions f in L2 of t whose negative Fourier coefficients vanish. Fourier coefficients vanish for all negative n. Or equivalently, this is the closure of the linear span of all the functions En, where n is non-negative. So this is a closed vector subspace of L2 of t. By the way, there is another definition of the Hardy space which emphasizes its complex analytic flavor. It can be shown that each function in Ht can be holomorphically extended into the unit disk. But at this point, this is not essential for us.
So I did a course in Libreus 2, and we had some problems with Hardy space, but it was defined in some different way. So the scalar product the inner product was defined as psi times psi bar, and also times 1 minus the modulus, square modulus of this function. No, square modulus of z, that's some power, and then integrate over the whole disk. So it is some other Hardy space, or are these some kind of somewhat equivalent, or do they look like each other?
maybe I didn't completely catch your definition. So in your definition, it's a subspace of L2 on the disk, or still of L2 on the circle? On the disk. Well, we can define it in a different way as a space of functions on the disk. But the inner product, well, maybe this is the same. I don't see it immediately from your definition. Actually, there are several equivalent definitions for the hardware space. For example, we can define it as the space of those analytic functions on the disk, for which the L2 norms over the circles of radius strictly smaller than 1 converge to some limit. And this will be equivalent. But this is not the same, this is not exactly the same which you have just said. But I don't know, maybe this is equivalent because this is a classical object, and it's typical for classical objects to have several equivalent definitions. This is only one of them, maybe. For the theory of Topless operator, this is more convenient. But for some complex analytic questions, of course, it is not very suitable. Maybe if you show me later or just send me by email your definition, maybe I'll find you some reference where the equivalence is proved. But I don't see it immediately it's not immediate from the definition. Okay, so the hardware space is a closed vector subspace of L2 on the circle. So we can take the orthogonal projection onto the hardware space. And this projection will be denoted by big P. So we denote by big P the operator on the L2 space, which is the orthogonal projection onto H2. That is the projection onto H2 along its orthogonal complement. This is the so-called Riesz projection. This is not the same Riesz who introduced compact operators, but this is his brother, Marcel Riesz. Of course, this looks like something trivial, but Marcel Riesz was interested in LP, where P is different from 2. And this is quite non-trivial in this case. But we will be interested in the L2 space. Okay, now we are ready to introduce Topless operators. So some more notation. For each essentially bounded measurable function f on the circle, we denote by mf the respective multiplication operator which acts on the L2 space. This is the multiplication operator, a very classical object. So now what we're going to do is to construct a certain operator on the hardware space out of MF. So we define the Topless operator, with symbol f. F is still a bounded measurable function. As follows, this is an operator. This operator acts on H2. And this operator is defined as follows. First, we restrict the multiplication operator to the hardest space. But in general, there is no reason for the hardest space to be invariant under this operator. So if we want to come back again to the hardest space, we just compose this with P. And we get an operator on the hardest space. So in operator theory, such operators are called compressions. So this is the compression of the multiplication operator to the hardest space. We restrict, and then we compose with the orthogonal projection. So our goal will be to find a reasonable condition under which this operator is Fredholm, and to give a geometric interpretation of its index. First of all, we have the following proposition. By the way, this operator is defined for each essentially bounded measurable function, but from now on we will concentrate on the special important case in which the symbol is continuous. Some of our results extend to the general case, but we will be interested in the continuous symbols. So first of all, I claim that for each continuous function f on the circle, the commutator of the Riesz projection and the multiplication operator, mf, is compact. The commutator is compact. And second, if f and g are continuous functions on the circle, then we have the following equality: Tf Tg equals Tfg. In general, this is false, but this is true modulo the compact operators. And it is good that this is false literally, because this abstraction for this equality, for the exact equality, plays a fundamental role in extension theory, which is closely related to K-theory of operator algebras. Okay, to prove part one, we do the following trick. We denote by A the set of those continuous functions on the circle for which this commutator is compact. So we want to show that A actually equals C of t. So it's clear from this definition that A is a closed vector subspace of C of t. Is a closed vector subspace. And clearly it contains the function which is identically 1. Because if f is identically 1, then this is just the identity operator. I claim that A is actually a subalgebra of C of t. Well, indeed, if f and g are in A, we can calculate the commutator of P and MFG. MFG is, of course, MFMG. And it's a well-known algebraic fact that the commutator with a fixed element in any associative algebra is a derivation of this algebra. So we use the following Leibniz identity. But this operator is compact because f is in K, f is in A, and this operator is also compact because G is in A. And so this implies that the whole expression is compact. So we conclude that A is a subalgebra. A is a subalgebra of C of T. Now, in order to show that A is just C of T, we again use the Weierstrass theorem. This space is dense. But since En is E1 to the power n, it's enough to show that E1 and E minus 1 are in A. And this is an explicit computation. So if we calculate the commutator of P and M E1, so M E1 is just the multiplication by the coordinate, then the result will be as follows. This operator, the action of this operator on our trigonometric basis looks as follows. It takes EI to 0 unless I is minus 1, and to E0 if I equals minus 1. This is E0 and is 0 otherwise. This is a little exercise for you, just an elementary computation. So we see that this commutator is a rank 1 operator. Its image is one-dimensional. So of course it is compact, and so E1 belongs to A. And a similar argument shows that E minus 1 belongs to A. So since A is an algebra, we conclude that E to the power En, which is E1 to the power n if n is positive, or E minus 1 to the power minus n if n is negative, are also in A. So this implies that En belongs to A for each n. And now Weierstrass theorem implies that I is C of T. And this completes the proof of part 1. So we see that this commutator is always compact. Now part 2 easily follows from part 1. So let's take TFTG. TFTG. So by definition, this is PMF, PMG restricted to H2. Yeah.
What is the commutator of P and doing nothing?
It is not doing nothing. Multiplication by 1 is the identity operator. Where's it? Oh. Multiplication by 1 is the identity operator. It takes G to itself. And it commutes with everything.
So the commutator is 0.
Commutator is 0. 0 operator is compact. Okay, so this is the composition, the product of two Topless operators. Let's now look here, M, F, and P. So by part 1, we can interchange these two operators up to some compact perturbation. So by part 1, this is P, P, MFMG modulo the ideal of compact operators. And that's it, because PP is P is a projection, so P squared is P. MFMG is MFG. And this is our definition of the Topless operator, TFG. So this completes the proof. By the way, let's observe that the second part of our theorem means that we have an algebra morphism. An algebra homomorphism from C of t to the Kalkin algebra of the Hardy space, which takes f to tf plus k. This is just an equivalent form of the second part of our result. Okay, now we're ready to prove the index formula for Topless operators. Before we formulate it, let's recall some standard facts from elementary topology. So we introduce some notation. We use the following notation to denote the set of homotopic classes of continuous maps from the circle to the punctured complex plane. Homotopic classes of continuous maps from the circle to C minus 0, to the punctured complex plane. Well, as usual, the square brackets denote the set of homotopic classes. It's a standard fact from elementary topology that there is a bijection between this set and the integers. There is a bijection that's denoted by alpha between this set and the integers, which takes each En. So En is En of z is z to the power n. It takes En to n for each integer n. This is a standard fact of elementary topology. It is closely related to the fundamental group of the punctured complex plane, but it is not exactly the same, because when we speak about fundamental group, the fundamental group involves the base point. And the homotopy is considered in the class of those paths which respect this base point. And here we have all continuous maps to the punctured plane, to the punctured complex plane, but the result is the same. So the set of homotopy classes is bijectively corresponds to the integers. And we introduce the following standard terminology. For each continuous function f on the circle, continuous non-vanishing function s on the circle, f on the circle, the winding number of f is denoted by w of f, and this is nothing but alpha applied to the homotopic class of f. In Russian we sometimes say вращение или число вращения. Тут разные есть переводы, но по-английски чаще всего говорят winding number. sometimes, by the way, sometimes the winding number is called the index of f around 0. And this is a beautiful place where two different meanings of the word index correspond to each other. Namely, we have the following result: the index formula for Topless operators. For each, I claim that for each non-zero, non-vanishing continuous function f on the circle, the corresponding Topless operator Tf is Fredholm. And the index of this operator equals minus the winding number of f. Okay, so first of all, why is it Fredholm? Well, f is no way of vanishing. So f is an invertible element of the algebra C of t. But we have just observed that we have an algebra homomorphism from C of t to the Kalkin algebra, map which takes f to tf plus k is an algebra homomorphism to the Kalkin algebra. In particular, it takes invertibles to invertibles. It is a unital algebra homomorphism. So it takes invertibles to invertibles. So this element is invertible, but this means exactly that the operator Tf is Fredholm. Tf is Fredholm. Okay, now let's calculate the index. Well, since alpha is a bijection, we see that WF is, let's just denote W of f by n. Let n denote W of f. Then since alpha is a bijection, we conclude that f is homotopic to En. F is homotopic to En. And let's now draw the following picture. So since they are homotopic, we can find a continuous path, gamma, in the space of all non-vanishing continuous functions on the circle. There is a continuous map gamma such that gamma connects f with En. This is a homotopy between f and En. This is not the end of the picture. Now we have a continuous map from this space to this space, to the set of Fredholm operators on the RD space, which takes f to Tf. Clearly, this is a continuous map. And we have the index map, which is also continuous because it is locally constant. So the composition is a continuous map from the interval to the integers. But a continuous map from the interval to the integers is a constant. So we conclude that the index of TF equals the index of TEN. And the index of TEN is easy to calculate explicitly. So let's consider a left shift operator and a right shift operator on the little L2 space. TL and TR. For convenience, we let them act on the little L2 space over the non-negative integers, for the reason that the orthonormal basis of the hardest space is indexed by non-negative integers. So let TL and TR be the left shift operator and the right shift operator. I claim that for each integer n, the operator Tn on the hardest space is unitarily equivalent to Tr to the power n if n is greater than or equal to 0, and to Tl to the power minus n if n is negative. Well, indeed, if we look at the action of this operator on the basis of the hardest space on Ek, well, if k is if n is greater than or equal to 0, then it takes Ek to En plus k by construction, and this coincides with the action of the right shift, or the nth power of the right shift, on the standard basis of this space. So if we identify this space with the hardest space by taking the trigonometric basis of the hardest space to the standard basis of this space, then we get a unitary equivalence between this operator and this operator. And the same result holds if n is negative. If n is negative, then the operator Ten, it's the compression of the multiplication operator. So the multiplication operator takes Ek to Ek minus n. But Ek minus n is sometimes in the orthogonal complement of the hardest space. Namely, it will be in the orthogonal complement if n is bigger than k. And so it is 0 if n is bigger than k, and is k minus n if n is smaller than k. So, but this is nothing but the action of this operator on the little L2 space. So these operators are unitarily equivalent, and their indices are the same. But if n is non-negative, then the index of this operator is minus n, because the index of the right shift is minus 1. And the index of the left shift is 1. So the index of the minus nth power of the left shift is minus n. So in both cases, we get minus n. That is minus W of f. And this completes the proof. Okay, so this nice geometric formula for the index of Topless operator has many interesting generalizations. So on the one hand, Topless operators can be generalized to the setting of several complex variables. And so we get Topless operators in several complex variables. And on the other hand, they can be generalized in slightly different direction. And another natural generalization leads to this oracle called Wiener-Hopf operators. And there is also a nice Fredholm theory for such operators. Okay, so that's all for today. And this is the end of our story about Fredholm operators. So at the next 2 to 3 lectures, we discuss some basic facts on topological vector spaces. This will be, first of all, this is useful for many reasons, but we will use these facts later when we discuss spectral theory of self-adjoint operators on a Hilbert space. And most probably we will have a midterm exam on the 16th of March, so in 2 weeks. I'll put the program in a few days on the website of the course. Okay, thank you. Сейчас я только сниму это оборудование. У вас, кстати, ну, не знаю, наверное, надо. Я все равно по e-mail, конечно, буду спрашивать. Там 16-го никаких нету мероприятий обязательных. Там вот 16, ну, через 2 недели. Чтобы не совпало ни с чем случайно. Ну да. Ну да, поскольку на разных курсах по-разному, конечно. У меня было 2 варианта, либо 16-го, либо 30-го. Но 30-го это уже сессии, там, я боюсь, наверняка будут какие-то другие контрольные мероприятия, и сразу, в общем, окажется, что всем неудобно. Так что, наверное, лучше. Это же по гифту берется, а не по окружности. Возможно, это считать надо, конечно.
Нет, там условия на коэффициент этих функций, когда в прошлом месте была задача, что суммируем интеграл по окружности, меньше там получалось, что коэффициент должен быть из 2.
Да,
есть другое, там коэффициент должен быть просто из 2, но коэффициенты разделить на какие-то окружности тоже.
Ну, то есть, по-разному. А если единичка?
Если единичка, то это просто обычная, просто интеграл квадрат.
Ну, а условия коэффициент фурье? Условия коэффициент фурье? Ну, плохо вы знаете. Надо посчитать, конечно. То есть это, в общем, чуть-чуть похоже, конечно, но все-таки когда по кругу дается. Ну, оно много где появляется, да. На самом деле, оно тут вот уже у вас эта технология возникает, следующий яд. На самом деле, вот эти пространства, пространство аналитических функций, они все ассоциированы с такими вот функциями Homotopian, с следующими ядами, они, в общем, разные бывают, но это как раз такой типичный инструмент, много где возникает, представление там, в разных аналитических вещах, в общем, такая вот полезная. Вот. То есть, может быть, это и не дословно пространство, плохо знать. Надо посмотреть, что условия, если говорить, что там все условия на коэффициенты возникают, это значит, что это условия надо. Вот. Но это вот что-то такое вот из истории серии пространства гибридов пространства